let's calculate the line of intersection between two planes. I have planes plane 1 and plane 2 right here. They have normals that are not multiples of each other, so these planes are not parallel. And if they're not parallel, they're going to intersect in a line, like the spine of a book. So I have two normal vectors, and if I cross the two normal vectors of the planes, I will drive in the direction of L. So we calculate cross product of N1 and N2 by covering up in the first slot. 12 minus 10 is 2. In the second slot, covering up, I have -3, subtract 20, it's -23. But I take the positive version of that, I take the opposite in the J slot. And then here I have 1 minus -8 is 9. And this was the easy part, the direction vector for this line. So the equation of that line L, parametrically, x, y, and z. The direction vector, 2, 23, and 9. Comes parameter t. What I need now is some point on the line to act as a base point of the line. But the problem is, I don't know a point that's naturally on the line, and I can't easily find it by inspection. So I want to add some point x naught, y naught, z naught that belongs to both planes. If I find a point that belongs to both planes, then it will be on the intersecting line, and I'll be done. But I need to do some work to find this x naught, y naught, z naught. So how do you find a point that satisfies both of these equations right here? I literally have to solve the two equations and the three unknowns. So let me name these equations, not the planes, but name the equation 1 and equation 2, just so I can work on them. And the way I'm going to work on them is by eliminating variables until I've gone as far as I can. In algebra class, this might be called row reduction. So if I take -2 copies of equation 1, dump it on equation 2, I change the system to this. First equation untouched, but second equation, add 2 copies negative of the first equation. 0, 9, -23, and -8. No x's, 9 y's, minus 23 z's, and -8. There's a z right there I left out. Okay, now I'm going to find out what I need to do to isolate this y. I want to get rid of this y right here. So I have x and y isolated. So first I'm going to divide the second equation by 9. Rewrite the whole system. Divide the second equation by 9. And fractions are going to be unavoidable. But now I can take 4 copies of this equation to eliminate this y. Again, think of this as first equation, second equation, just for the work. I'll take 4 copies of the second equation, add it to the first equation, and this is what I get. 4 copies of nothing plus x is just a single x. 4 copies of this added onto this is no y's. 4 copies of this, minus 92 over 9. Of course, this is 90 over 9. So I get minus 2 over 9. 4 copies of this is negative 32 over 9. This is 63 over 9. 63 minus 32 is 31 over 9. Together with the second equation, I've now taken this system of two equations and two unknowns as far as I can take it. I know what x and y are isolated, but there's nothing I can do to isolate or eliminate the z. I can't take it down to a single value. So I have to say x and y are things that depend on z. And every time I pick a different z, I get a different x and y. Now you write this in the language of systems of equations with a parameter. You'd say the solution to this system of equations in plane 1 and plane 2, add the z parts over to the other side, choose a parameter to take the place of z. You can say 2/9 t was 31/9. Y is 23/9 t. Minus 8/9. And z, which is not constrained or described in terms of the other variables, z is free to be anything I please. I'll let that be the parameter t. So once I choose t, I get x and y and z. So if I just set t equal to 1, there's no convenient number. I think I could take no convenient number to make this not fraction. So I'll just take t equal to 1. And that'll give me a point on that line. Any value of t will give me a point on that line. So I'm going to use the point 1 for z. 23/9 minus 8/9 is 15/9. And 2/9 times 1, 2/9 plus 31/9 is 33/9. Now this is just an equation of a line that goes through that intersection. I could change the direction vector. I could find a different point. And the base point here is the messy thing. I would feel more comfortable if I knew that this point, 33/9, 15/9, 1, was truly on those planes. So let's check by bringing those numbers over here. In the first equation, that would be 33/9 minus 60/9 plus 10 times 1, 10, which is 90/9. And that adds up to what? 123/9 minus 60/9. That's 63/9. So yes, that point lives on that plane. Does that point live on this plane? Insert the numbers. 66/9 plus 15/9 minus 3 times 1, which is minus 27/9. And what does that add up to? 66 and 15, 81. 81 minus 27, 54. 54/9 is 6. So that point actually lives on both planes. That makes it inside the intersection line L. This is the direction vector for that line. And that's from the cross product. So this is a legitimate description of the intersection of those two planes.